You know that feeling, right? You're staring at your screen, watching your code just crawl, especially when it's doing the same thing over and over. What if you could give your code a memory so it never has to do the same work twice? Well, that's exactly the secret we're unlocking today.
All right, so here's our game plan. We'll kick things off by digging into the real problem, that high cost of repetition. Then we'll look at the solution, caching, and Python's amazing decorator for it. After that, we're getting practical. We'll cover how to make caches stick around between runs and what the pros do. And we'll wrap it all up with one final crucial rule, caching wisely.
Okay, so let's start at the very beginning with identifying the actual problem. It is shockingly easy to write code that gets bogged down doing the same heavy lifting again and again. And that kind of inefficiency, it's a silent killer for performance.
Have you ever written a function that just feels slow? You run it once, it takes a second, you run it again with the exact same inputs, and it's just as slow. You're not alone, and believe me, there's usually a very clear reason why this is happening. Let's take a look at a classic example here, a simple recursive function to calculate Fibonacci numbers. Now, this function is what we'd call computationally expensive. It works, sure, but it does it by calling itself over and over again, which creates this massive, totally unnecessary workload. And here is where it all falls apart. To get fib of 5, the code has to call fib of 4 and fib of 3. But wait, fib of 4 also has to call fib of 3. Right there, we're already calculating the exact same value twice. And this waste, it just explodes exponentially as the numbers get bigger. The computer spends nearly all of its time redoing work it's already solved.
Just look at this difference. It's night and day. The first time we call our function for fib 30, it takes almost 3 seconds. But if we could just remember that result, the second call is, well, it's basically instant. That right there is the power we're about to harness.
So how do we actually get that incredible speed boost? That brings us right to our next section, the caching solution. The idea at its heart is so simple. Remember, don't recompute.
The official term for this technique is memoization. Now, it's kind of a fancy word, but it's for a beautifully simple idea. We're basically giving our function a memory. We store the results of those really expensive calls, so the next time we ask for the same thing, the function just says, oh, I know this one, and gives us the answer right away.
And what's so cool is how simple this is deep down. You can actually build a basic cache yourself with nothing more than a standard Python dictionary. Before doing any real work, the function just checks the dictionary. Hey, have I seen this input before? If it's there, boom, it returns the stored value instantly. If not, okay, it'll do the work, but then it saves the result for next time.
But hey, this is Python we're talking about. So you just know there's a cleaner, more, well, Pythonic way to do it. And that brings us to Python's bit of magic, the power of the @LRU cache decorator. So first, what exactly is a decorator? Well, think of it like a wrapper. It's a special function that you can wrap around another function to add new behavior, all without ever touching the original code. You can always spot them by that little @ symbol right above a function definition.
And here it is. This is the magic trick. We take our slow, clunky Fibonacci function, we import LRU cache, and we add just one single line of code on top of it, @LRU cache. That's it. Seriously, Python now handles all of that memoization logic for us. It's clean, it's readable, and it is unbelievably powerful.
But what does that LRU part actually mean in @LRU cache? It stands for least recently used. See, a cache can't just grow forever. It needs a rule for what to throw out. An LRU cache is smart about it. It doesn't just kick out the oldest stuff, it kicks out the stuff that hasn't been used in the longest time. The idea is what you used recently, you're probably going to use again soon. So we've totally mastered in-memory caching. It's amazing. Right up until our program stops running. Then what? Well, that brings us to a really critical real-world problem. How to cache between program runs and make our results stick around.
Yeah, this is a super important and practical question for any developer. In-memory caches are fast, no doubt, but they get completely wiped every single time your script finishes. So what do you do if you're building a tool that needs to remember results from the last time somebody ran it?
This whole problem was just framed perfectly by a developer on Reddit. They asked, I've got some local code that caches in a .cache folder,
and I'm looking for some best practices. They want to publish their awesome code as a library for others to use. But how do you properly handle a cache that has to live on somebody else's computer?
One really powerful way to solve this is with a custom decorator that saves results to a file instead of just keeping them in memory. Using a library like Pickle, it can check for a cached file on your disk before it even runs the function. If the file's there, it just loads the answer. If not, it does the work, saves the result to a new file for next time, and then returns it. And just like that, our cache is persistent.
Okay, so now that we know how to create a cache that sticks around, let's talk about how to do it responsibly. It's time to dig into some real-world best practices with advice straight from the developer community. If you're going to ship a library, you have to be a good citizen on your user's machine. So, first off, namespace your cache. Don't just dump a generic .cache folder in their home directory. Give it a specific name. Second, make it configurable. Let people choose where the cache goes. Third, have a fallback plan. If for some reason you can't write to the main spot, fall back to a temp directory. And finally, a pro tip. Use a helper library like platform_dir. It'll figure out the correct cache path on any operating system, automatically. And here is a hilarious but absolutely vital reminder of why this stuff matters so much. As one very frustrated Reddit user put it, I have some applications that have burdened my laptop with dummy folders. It's honestly just fucking annoying. Don't be that developer. Be respectful. Manage your cache responsibly. We've seen just how powerful caching can be. But you know what they say? With great power comes great responsibility. And this brings us to our final and maybe most important section. Cache wisely. So with this awesome new superpower in our tool belt, the temptation is definitely there. You have to ask, should you just cache everything? I mean, if it makes things faster, why not just sprinkle it everywhere? Well, because optimization has an order of operations. The great computer scientist Joe Armstrong put it perfectly. Make it work, then make it beautiful, then, if you really have to, make it fast. Caching is a tool for that very last step, making it fast. And that means it should probably be the last thing you reach for, not the first. And that is the final, most important rule of all. Don't guess. Profile your code first. Use the tools to find the actual performance bottlenecks in your program. Find out where your code is really spending all its time. Then, and only then, do you apply caching wisely. That is how you truly go from slow code to lightning fast, the right way.